Let us solve Fourier transform for a rectangular pulse. So we take a rectangular pulse of width tau, so which is existing from minus tau by 2 to tau by 2. So this is x of t, and let us take the strength is 1. So I will represent the signal as rectangle function of t by tau. Okay, so let us find out the Fourier transform of this function. So as you all know that the Fourier transform expression is x of omega equal to integral minus infinity to infinity x of t e power minus j omega t dt. You know that this pulse is from minus tau by 2 tau by 2. So we are defining the limits of this pulse, and the strength is 1, and remaining thing e power minus j omega t dt. Okay, so this one will be in the integration e power minus j omega t by minus j omega minus tau by 2 to tau by 2. So let us substitute this upper limit and lower limit. So you will get e power j omega tau by 2 minus e power minus j omega tau by 2, and we have the denominator j omega. I am changing the terms, okay, minus term. So this thing, you can write this expression in terms of sine. Okay, that is sine theta. You know that e power j theta minus e power minus j theta by 2j. So we are going to convert this entire expression into the sine terms. So we need the denominator 2j. So we have to multiply the denominator with 2. So 2 into e power j omega tau by 2 minus e power minus j omega tau by 2, that is 2j. I am bringing this omega to outside of this expression. So this will be equal to 2 by omega sine omega tau by 2. Okay, so we are rewriting this entire expression as sine omega tau by 2. So we can again change this expression in terms of sinc function, that is sine x by x, a sinc function of argument x, like this. Okay, I want to convert this sine expression, sine omega tau by 2 expression into a sinc x. So we need the denominator, we need the tau in the denominator also. So for that one, we make 2 by 2, so 2 by omega sine omega tau by 2, and we will make it like this, tau and tau. So I bring this omega and 2 to inside this term. So tau sine omega tau by 2 omega tau divided by 2 multiplied with tau. So this thing will be tau sinc omega tau by 2. Okay, the term will be tau sinc omega tau by 2, and this is the Fourier transform of your pulse. Okay, so In a rectangular pulse having width tau, the Fourier transform will be tau sinc omega tau by 2. If the strength is 1, it is multiplied with just there is a strength 1. So if there is a, you can multiply with this like this. Okay, and this one is an important transform. Okay, the Fourier transform of a rectangular pulse is a sinc function. Okay, and this sinc function will be 0 when omega tau by 2 is plus or minus n pi. Okay, that is the sinc the sine omega tau by 2 will be 0 for omega tau by 2 is plus or minus n pi. Okay. So this is one method, a general or traditional approach to find the Fourier transform of a rectangular pulse. There is another approach where you can use the property to find out the Fourier transform of this rectangular pulse. Okay, so evaluate the Fourier transform of rectangular pulse using Fourier transform property. Okay, let us see this. So let me draw this once again. So of t 1 minus tau by 2 to tau by 2, and this is 0. Now I will find out the derivative of this x of t. Okay, the derivative of x of t. So the derivative of x of t is, I'm finding out the d by dt of x of t. D by dt of x of t. That is, I'm going to find the change in x of t with respect to time t. Okay, or the time axis. Let me find out the change of x of t with respect to t. Okay, so from minus infinity to minus tau by 2, there is no value, that is there is no change, so the change is 0, the value is 0, that indicates there is no change. But at the instant of minus tau by 2, there is a change of value from minus tau by 2 to 1. So I represent the change of x of t at minus tau by 2 as this one. Okay, that is the value is changing from minus tau, so the value is changing from 0 to 1 at minus tau by 2. So I represent the change at minus tau by 2 from 0 to 1. Okay, from minus tau by 2 to tau by 2, the value is constant, that is there is no change, the x of t is constant, no change. No change means I am going to represent the change is 0, so the value will be 0 at this position. Okay, the value will be 0, that is change is 0, change is 0 from minus tau by 2 tau by 2. Okay, after reaching tau by 2, there is a change of value from 1 to 0, that is the change is negative or strength minus 1. Okay, this indicates the change of x of t with respect to t. So I can write this d by dt of x of t as in terms of impulses, that is impulse at minus tau by 2 and impulse at tau by 2. Yes. The strengths are 1 del of t plus tau by 2 minus 1 del of t minus tau by 2. These two are impulses at the positions minus tau by 2 and tau by 2. Okay. Now I will apply the Fourier transform property, the time differentiation property. The time differentiation property. That is applying the Fourier transform. So d by dt of x of t, you know the property j omega x of omega. And the Fourier transform of these impulses, time shifted impulses, are e power j omega tau by 2 minus e power minus j omega tau by 2. Okay, frequency shifting property. Okay, so we know that x of omega is the Fourier transform of x of t. That is x of omega equal to e power j omega tau by 2 minus e power minus j omega tau by 2 by j omega. So again we have to do the same procedure what we done before, converting this expression into sine term and later going for the sin term. Okay, and so this will be, this 2 by omega sine omega tau by 2 and again tau sin omega tau by 2. It is so this is the procedure of finding out the Fourier transform of a pulse using differentiation property, the time differentiation property. So let me solve another one, the pulses positions. So we consider two pulses at two positions, and this is x of t, and this is minus 4, minus 2, and 2. Two pulses in the durations minus 4 to 2 is one pulse, and 2 to 4 another pulse. The strengths are same. The strengths are 1. So you can go for the traditional approach, or else you can go for the time differentiation property. So let me draw the derivative of x of t. It is minus 4, minus 2, 2 and 4. So there is a change of value at minus 4 from 0 to 1. So I indicate an impulse like this, strength 1, and the change is 0. Okay, the change is 0. The value is constant, the derivative of that constant is 0 in a mathematical way. So we go for 0 only. This 0, that is 0. From minus 4 to minus 2, the value is 0. At minus 2, the value is decreasing to 0, that is 1 to 0. So we represent the decrease of value minus 1. And now from minus 2 to 2, the value will be 0. And at 2, there is an increase in value, that is from 0 to 1. So we represent with an impulse, and the value we constant in between 2 to 4. So the derivative is 0. And again at 4, there is a decrease of value from 1 to 0. So we represent like this. Now we represent this one d by dt of x of t and impulses, the four impulses at locations -4, -2, 2 and 4 with strengths 1. So 1 into del of t plus 4 minus 1 del of t plus 2 plus 1 into del of t minus 2. So this value is minus 1 minus into 1 into del of t minus 4. Okay. Now again apply the Fourier transform in both sides. You know this j omega x of omega. So applying the time shifting property, e power j 4j omega minus e power 2j omega plus e power minus 2j omega minus e power minus 4j omega. So you can write these terms into sine terms and again sin terms. It is x of omega equal to e power 4j omega minus e power 2j omega plus e power minus 2j omega minus e power minus 4j omega by j omega. So let me distribute this one. E power 4j omega minus e power minus 4j omega by j omega plus e power. Okay, so let me write this minus here, minus e power 2j omega minus e power minus 2j omega by j omega. So splitting these terms, so let me multiply with this 2 by omega. So I can write this as, so I'm writing 2 so sine 4 omega minus 2 by omega is equal to sine 2 omega. 8 sine 4, sorry, sin 4 omega minus and this one will be 4 sin 2 omega. Okay, so this one will be your x of omega.
Let us solve the Fourier transform of triangle which is having the width of tau. So like as the Fourier transform of pulse, we perform the time differentiation property to find out the Fourier transform of the triangle. Let me draw the triangle. So you can solve this by considering the line equations also, minus tau by 2 and tau by 2. I am considering this peak as A and this is x of t. So we have to find out what's x of omega, that is Fourier transform. In generally, the Fourier transform we can perform by using the traditional equation e power minus j omega t dt minus infinity to infinity. So you can write the line equations of this one and this one in the durations of minus tau by 2 to 0 and 0 to tau by 2. So we can take like minus tau by 2 to 0, that is x of t e power minus j omega t dt plus 0 to tau by 2 x of t e power minus j omega t dt. So in the duration of minus tau by 2 to 0, the line equation, okay, the line equation is, you can perform like y equal to mx plus c, okay. So between minus tau by 2 to and 0, this y will be, that means the slope, that is, you can find out the slope like opposite side by adjacent side. The opposite side will be a by the slope is tau by 2, okay, and this is the positive slope, and this is the x is t plus the y-intercept is a. So you can write this as 2at by tau plus a, okay, and this is x of t, y-axis. So the y-axis, sorry, the line equation in the duration of minus tau by 2 to 0, you have to substitute this one. So you can take this one as x1, okay. So minus tau by 2 to 0 x1 of t e power minus j omega t dt plus, in between 0 and tau by 2, let us consider that one as the x2 of t, that is, again the slope will be negative slope, so minus the same slope you will get, that is a by tau by 2, so we will get 2at by tau plus a, okay. So you substitute this one at 0 to tau by 2 x2 of t e power minus j omega t dt. So like this you can perform in a traditional way by using the line equation approaches, so that you can get the Fourier transform x of omega. And there is another approach, the second approach, using the differentiation. Another approach using derivative of x of t, okay. So what we done in the previous one, so let us solve this one by using the derivative. I am again taking the triangle, x of t minus tau by 2 to 0 and 0 to tau by 2, and this is the signal. So first find out the first order derivative, that is d by dt of x of t. So already we discussed that d by dt of x of t is, we have to find out, we have to plot the change of x of t with respect to t, okay. So plot change of x of t with respect to t. So I am taking the limits, the signal duration. So let us plot the change. So the change is, this is a line that is moving in this way with a constant slope, okay. So from minus tau by 2 to 0, the x of t was changing in the same way, that is it is maintaining a constant slope. Okay, it is maintaining a constant slope, that is from minus, the change is the slope, that is from minus tau by 2 to 0, it had the constant slope. Okay, it had the constant slope, that is you are mentioning the change, that is the slope. So what's the slope? The slope is opposite side by adjacent side, so it is a positive slope. Okay, it's a positive slope, it's increasing, the signal was increasing. Okay, the signal was increasing with a constant slope, so that's why I am representing a constant value in between minus tau by 2 to 0. So this strength will be, this value will be the slope, which is a by tau by 2, that is 2a by tau. Okay, so 2a by tau, the value, this value will be 2a by tau. Okay, and now from 0 to tau by 2, the signal was moving in this direction. The signal was moving in this direction, that is the signal was decreasing by maintaining a constant slope. Okay, by maintaining a constant slope. So I will mention this as it have a negative slope, the value was decreasing. Okay, the value was decreasing and the slope was constant. So I will write this one like this. It has a negative slope, that is minus 2a by tau. Okay, so here I am mentioning the change of x of t with respect to t. I am plotting the change of x of t with respect to t, that is the slope values. And after this I am going to do another differentiation for the above signal. Okay, that is d square x of t by dt square, the second order derivative. So now this plotting change of derivative of x of t with respect to t. Okay, now I am plotting the change in d by dt of x of t for the above signal. So that is from minus tau by 2 to tau by 2. You can observe that the value was increasing like this and this is constant. So I will mention the rise as like this and the derivative of constant is a 0 value. Okay, and this rise will be 2a by tau, this impulse. And from minus tau by 2 tau 0, the value was constant. So the derivative of that constant is 0. And if you observe at the position of 0, the value was decreasing from 2a by tau to minus 2a by tau, that is the value will be 4a by tau. Okay, at 0 the value will be 4a by tau and that is a negative value. There is a decrement of value from 2a by tau to minus 2a by tau. The total will be minus 4a by tau. Okay, minus 4a by tau. So we are observing an impulse at minus tau by 2 and 0 and again the rise of value at tau by 2. So this will be 2a by tau. Okay, and I am going the value from minus 2a by tau to 0, that is the value is increasing. So I represent the change with a positive impulse. Okay, now let us, and this will be 0 for the constant. Now let us plot this one, right? This expression d square x of t by dt square, and this will be impulse at minus tau by 2 with strength 2a by tau. So 2a by tau del of t plus tau by 2, and at 0 the impulse strength was minus 4a by tau del of t, and at tau by 2 the impulse strength was 2a by tau, that is del of t minus tau by 2. Okay, so we got an expression which represents the second order derivative of x of t in terms of impulses. Okay, x of t is triangle, x of t is a triangle, but the second order derivative of x of t is an impulses like this. Okay, so here we use the properties, the Fourier transform properties for this one. So I apply Fourier transform for both sides. So Fourier transform of d square x of t. Okay, Fourier transform. So Fourier transform of d square x of t will be j omega square x of omega. The Fourier transform of impulse, you know this by applying this time shifting property. So the strength was 2a by tau, that will be e power j omega tau by 2 minus 4a by tau. The Fourier transform impulse will be 1 plus 2a by tau, and again an exponential e power minus j omega tau by 2. So I will rewrite this expression as 2a by tau. So I will get a sine function here. So 2a by tau e power j omega tau by 2 plus e power minus j omega tau by 2 minus 4a by tau. So this will be j square is minus, so right, j omega square x of omega. So I will bring this j omega square to the right hand side. So you will get minus 2a by tau omega square e power j omega tau by 2 plus e power minus j omega tau by 2 plus 4a by tau. Okay, so this entire expression I can make it as 2a by tau omega square, and I will convert this one into the cos term. Okay, and I am moving, I mean this 4a by tau, I am making entire terms as a common expression. So minus 2 e power j omega tau by 2 plus e power minus j omega tau by 2 by 2 plus 2. Okay, and this will be 2a by tau omega square, and this will be cos omega tau by 2. So I will bring this 2 to the outside of this entire term, and I will write as 1 minus cos omega tau by 2. So this is your expression. Okay, about this is x of omega. So now let us change this 1 minus cos tau by 2 to the sine terms, and again sine to the sin term. Okay, this is your x of omega. So 4a by tau omega square, and this 1 minus cos omega tau by 2 will be 2 sine square, you know this trigonometric identity, omega tau by 4. Okay, 2 sine square omega tau by 4, and this is So this entire term you can write it as sine square. So in the bottom you should get omega tau by 4. Okay, so in the bottom you should get omega tau by 4. So I will write this 4 to the denominator side. So a by tau omega square, and to get the omega tau by 4 in the denominator, I will multiply with omega tau by 4 correspondingly. So sine square omega tau by 4 by omega tau by 4 square. So we have omega tau by 4 one term, and here omega tau by 4. Okay, so this term will be written as a tau by 2. This entire expression we can make it as, sorry, we got right, so 8. So we missed about this 8. Right, 8a by tau omega square. Right, so a tau by 2, we will get it as, okay, sine omega tau by 4 by omega tau by 4. So I will write this expression like this. Yeah. So your final expression will be a tau by 2 sin square, okay, sin square omega tau by 4. Okay, this is your the Fourier transform of what triangle. So that is x of omega will be a tau by 2 sin square omega tau by 4. So we can see for any pulse, rectangular pulse or also triangle, a rectangular pulse, a square pulse, the Fourier transform will be a sinc function. For a triangle, the Fourier transform will be a sinc square. Okay, a sinc square function, and this will be, I mean, by using this property you can easily find out the Fourier transform of a triangle, right? So this is the property what we are using to find out the Fourier transform of pulse and triangle by using the time differentiation property. Now let me solve another problem where we use the property of duality. Okay, so using duality property. So let us consider a problem x of t equal to 1 by t. Okay, so to solve some sort of problems we have to use the properties. So to use such properties you should be well aware of some transform pairs. Okay, so to solve this, the Fourier transform of x of t, we should get into mind about the 1 by t, I mean the formation of 1 by omega. So where we can find out 1 by omega in any Fourier transform pair. So the previous sessions we solved some problems like the Fourier transform of the signum function. Signum function Fourier transform is 2 by j omega. So let us use this property, so I mean this Fourier transform, and here I am using the duality property, that is x of t Fourier transform is x of omega, and capital X of t Fourier transform will be 2 pi small x of minus omega. Okay, so if you know x of t, if you know the Fourier transform x of t, that is x of omega, if in the place of omega, if you substitute with t, what will be the Fourier transform of that function, that x of t? That is, you can find out the Fourier transform easily by substituting omega, that is minus omega, in place of t. Okay, so here the signum function transform is 2 by j omega. Okay, so I will rewrite this one, sgn of t, Fourier transform is 2 by j omega. I will make it as j signum function of t by 2, the Fourier transform is 1 by omega. So I will use this one, and this is x of t and this is x of omega. Okay, so for x of t, what will be this one? Okay, this is 2 pi x of minus omega. So what is x of t here? X of t is 1 by t. The Fourier transform will be 2 pi x of minus omega. What is x of omega? X of omega is j by 2 sgn of omega. Okay, so I will substitute with minus omega, that is j by 2 sgn of minus omega. So 1 by t Fourier transform will be 2 pi j by 2 sgn of omega, that is j pi sgn of minus omega, and this is an odd function, signum function, so you will get minus j pi sgn of omega. So 1 by t Fourier transform will be this one. One by t Fourier transform will be this. So without knowing the duality property and the Fourier transform of signum function, you cannot find out the Fourier transform of 1 by t. Okay, so if you go for another one, Fourier transform of 1 by 1 plus t square. So for this one, I will recall that e power minus a mod t, the Fourier transform will be 2a by a square plus omega square. So we can compare this one with like this, your x of t. Okay, so if you substitute a value as 1, that is e power minus t, the Fourier transform will be 2 by 1 plus omega square. Okay, so e power minus mod t Fourier transform is 2 by 1 plus omega square. So I will bring this 2 to the right hand side. So e power minus mod t by 2, the Fourier transform is 1 by 1 plus t square, omega square. Now I use the duality property. So this is x of t and this is x of omega. So for x of t, okay, for x of t, the x of t is 1 by 1 plus t square. The Fourier transform will be 2 pi x of minus omega, that is 2 pi, we got right 1 by 2, 2 pi by 2 e power minus mod omega. So the Fourier transform of 1 by 1 plus t square is pi e power minus modulus of omega. So this is the Fourier transform. Okay, like this you can perform, you can solve the expressions, the Fourier transform expressions, by using duality property. Okay, right. So let me go for another one, the same I mean, we'll give a question like so this is some function like minus a minus b and minus b, sorry, plus b and a, and this is some constant x of t. So this thing you can perform the traditional way. I will go for the differentiation. So d by dt of x of t. So this one is the change of value from minus a to minus b. We represent with a slope, that is with a pulse. Okay, minus a to minus b. And minus b to 0, I mean minus b to plus b, the signal was constant, so the differentiation will be 0. From from plus b to a, the value is decreasing, and we represent with a slope like this, b and a. And we go for another derivative, d square of x of t. So we represent this pulse with a impulse like this and like this, minus a and minus b, 0, and at b there is an change of value from 0 to negative value, and at position a there is from negative to the positive value. We represent first like this. Okay. So we find out the impulse positions and their strengths, and we make it the expression d square x of t by dt square, okay, with the help of impulses, and apply the Fourier transform property. Okay, so like this you can solve numerous problems using the properties. Okay, so now I will go for application of another property like convolution. Consider x1 of t as e power minus 2t u of t and x2 of t e power minus 3t u of t. So I want to perform the convolution, the time domain convolution. Okay, so how to solve this one using Fourier transform property? You know this convolution property. In time domain, if it is convolution, in frequency domain it's a multiplication. So x1 of t convolution x2 of t, x1 of omega x2 of omega. Okay. So if you want to go for the time domain, you have to go for inverse Fourier transform of x1 of omega and x2 of, inverse Fourier transform multiplication of these two transforms, so that you can get the time domain expression finally. So let us find out first x1 of omega. x1 of omega is the Fourier transform of e power minus 2t u of t, and x2 of omega, the Fourier transform of e power minus 3t u of t. This is standard transform pairs we use here, 1 by j omega plus 2, and this will be 1 by j omega plus 3. Now let us multiply both of them, x1 x2, 1 by j omega plus 2, j omega plus 3. So we go for the partial fractions for the terms, and simply go for the cover up method, that is a by j omega plus 2 minus plus a by b, some other constant, j omega plus 3. So you have to find out what will be the values of a and b. So a value will be, simply use the cover up method, that is j omega plus 2 multiplied with 1 by j omega plus 2 j omega plus 3, and substitute j omega equal to minus 2. So where we get, for what value j omega plus 2 will be 0. So j omega, if j omega equal to minus 2, this term will be 0. Okay, so this will be, you will get minus 1. So a value will be minus 1, and similarly b value you can substitute, if it is a simple one, simple pole, plus 3 by 1 by j omega plus 2 j omega plus 3, and for what value j omega plus 3 will be 0, that is j omega equal to minus 3. So this will be, sorry, this one is the plus 1, right? A is plus 1 and b will be minus 1. So x1 x2 will be 1 by j omega plus 2 minus 1 by j omega plus 3. Okay. Now for getting in time domain, we perform the inverse Fourier transform, that is f inverse. Okay, f inverse of x1 of omega x2 of omega will be f inverse of 1 by j omega plus 2 f inverse of 1 by j omega plus 3. So we get e power minus 2t u of t minus e power minus 3t u of t, and this will be your convolution, x1 of t convoluted with x2 of t. So here we use convolution property, using convolution property. Okay, right. And another one, now we use, let us use to find out the responses of the systems by using these properties. So an input and output of a causal LTI system. Okay, a system response, a system was represented by using a differentiation or an LCCD expression. So input and output of a causal LTI system is related by d square y of t by dt square plus 5 dy of t by dt plus 6 y of t equal to x of t. This is a system representation. System representation in terms of input and output. Input is x of t and output is y of t. An LTI system description. So the task is to find out impulse response of a system. Impulse response of a system, of above system, and second one, what is the response? So what is the response of system if input x of t is t into e power minus 4t u of t. So we have to find out what is impulse response system and what is the response of the system if input is t e power minus 4t u of t. So again we go for the property applications. So we use time differentiation property here. So for the above one, that is d square y of t by dt square plus 5 dy of t by dt plus 6 y of t equal to x of t. Now apply the Fourier transform for this above expression, the time differentiation property. So d square means j omega whole square y of omega plus 5 first order derivative. So we will use just j omega y of omega plus 6 y of omega equal to x of omega. So I will convert this entire into y of j omega by x of j omega. So y of j omega by x of j omega, sorry, y of omega or y of j omega, I will write it as like this, y of omega by x of omega. This is nothing but a transfer function of the system. Okay, so 1 by j omega square plus 5 j omega plus 6. So if you go for the partial fractions and finding out the constants, you will get j omega plus 2 and j omega plus 3. I mean j omega plus 2 and j omega plus 3. You can write this expression, and the constants obtained by using the partial fractions 1 by j omega plus 2 and minus 1 by j omega plus 3. In previous problem we solved this one. So system transfer function is h of omega, that is 1 by j omega plus 2 minus 1 by j omega plus 3. We want the impulse response. Okay, we want impulse response, that is h of h of t. So I perform the inverse Fourier transform. So applying inverse Fourier transform for the above expression, that is h of n, you will get e power minus 2t u of t, e power minus 3t u of t, and this is the impulse response of the system. Impulse response of the system. So one first task was completed, and what's the second one means? Second one is what will be the output, that is what is y of t if x of t is, okay, if x of t is t e power minus 4t u of t, t e power minus 4t u of t. So for this one we have to go for the property application. You know h of omega, that is, sorry, you know h of omega is 1 by j omega plus 2 minus 1 by j omega plus 3. Okay, or else let me go for the above one, 1 by j omega plus 2 and j omega plus 3. This is, and this is y of omega by x of omega. So we have to find out what's y of t. We have to find out what is y of t, that is f inverse of y of omega. F inverse of y of omega. We know x of t and x of omega, that is Fourier transform of t e power minus 4t u of t. So we substitute this x of omega in the above expression h of omega. Okay, so x of omega, that is x of t, is t e power minus 4t u of t, and x of omega will be j d by d omega of 1 by j omega plus 4. Okay, that is t x of t Fourier transform will be j d by d omega of x of omega. We use this property. Okay, we use this property here. So here x of t is e power minus 4t u of t. While applying this frequency differentiation property. Okay, we are applying the frequency differentiation property. So you will get x of omega will be 1 by j omega plus 4 whole square. Okay, so we have the above expression, that is h of omega equal to y of omega by x of omega. So y of omega will be h into x, that is h is 1 by j omega plus 2 j omega plus 3 multiplied with x. What is x? X is 1 by j omega plus 4 whole square. Okay, so y of omega is 1 by j omega plus 2 j omega plus 3 j omega plus 4 whole square. Now I have to do the partial fractions for this one. This will be represented by a by j omega plus 2 plus b by j omega plus 3 c by j omega plus 4 d by j omega plus 4 whole square. So you can easily find out the constants of a, b and d. Okay, a, b and d. So a value will be, that is j omega plus 2 multiplied with y of omega at j omega equal to minus 2. Okay, so this will be 1 by minus 2 plus 3 and minus 2 plus 4 square. So you will get 1 by 3 minus 2 1, 4 minus 2 square 2 square, 1 by 4. So you will get 1 by 4. A value will be 1 by 4. So b will be j omega plus 3 y of omega j omega equal to minus 3, and this will be minus 3 plus 2 minus 3 plus 4 square. So minus 1 1, that will be minus 1. So b value will be minus 1, and you can perform the d. Okay, so d value is j omega plus 4 square multiplied with y of omega, and where j omega equal to minus 4. This will be 1 by minus 4 plus 2 minus 4 plus 3. This will be minus 2 minus 1. So 1 by 2. D value will be 1 by 2. So to perform C, we go for formula 1 by 1 factorial. Okay, 1 by 1 factorial, d by d omega of j omega plus 4 square y of omega, and you substitute j omega equal to minus 4 after applying the differentiation for the above expression. So 1 by 1 factorial 1, so d by d omega, so if you multiply with this one you will get an expression as j omega plus 2 and j omega plus 3. So substitute j omega equal to minus 4. So simply go for this differentiation and you will get a value like j omega plus 2 j omega plus 3 whole square, or else let me multiply this one. So d by d omega of 1 by j omega square plus 5 j omega plus 6. Okay, and d by d omega of j square minus 1 minus omega square plus 5 j omega plus 6. So this will be minus omega square plus 5 j omega plus 6 whole square and minus omega square plus 5 j omega plus 6, and the derivative of 1 will be 0 minus 1 into minus 2 omega plus 5j. Okay, so you will get 2 omega minus 5j and minus, so I will make this same, right? And I will write minus omega square plus j omega square plus 5 j omega plus 6, and in the numerator also I will write this 2 omega as minus 2 omega minus 5j, I will directly substitute j omega equal to minus 4, to j omega by j minus 5j by j omega square plus 5j plus 6 plus 5j omega plus 6. This will be substituting j omega equal to minus 4 into 2 by j minus 5j by j omega is minus 4, 16 minus 20 plus 6. This will be minus 8 by j minus 5j divided by 6 minus 4, 6 minus 4, 2. So you will get the constant c as like this. Okay, but let me write this c value as it is. So your y of omega will be a by j omega plus 2, this one, a by j omega plus 2 plus b by j omega plus 3 plus c by j omega plus 4 plus d by j omega plus 4 square. So a by j omega plus 2 plus b by j omega plus 3 plus c by j omega plus 4 plus d by j omega plus 4 whole square. So I don't substitute here ABCD, I'll directly take the inverse Fourier transform, applying the inverse Fourier transform. So a into e power minus 2t u of t plus b into e power minus 3t u of t plus c into e power minus 4t u of t plus d into, and in the denominator this is square, so you multiply with t e power minus 4t u of t. So this is your response y of t for the input t into e power minus 4t u of t. So y of t for input t into e power minus 4t u of t. So like this we have to perform or apply the Fourier transform properties to get the impulse response or response for any value or any input like this. Okay, so here you can remember one important property, that is differentiation in frequency domain. Those are t into x of t Fourier transform j d by d omega of x of omega. Okay, and if it is, there is an t power n, so that you can minus j t power n x of t Fourier transform will be d by d omega of x of omega. Okay, you can make this j power n to the right hand side. Okay, if there is a t power n to the left hand side, what will the expression? Okay, so you can use these properties while solving some problems, right? So these are the problems we come across in the Fourier transform or concepts while solving different problems in the Fourier transform. Importantly, you can use time shifting property, frequency shifting property, and convolution property, time differentiation, frequency differentiation. And these are the important properties you can use to solve several variety of problems, right? Thank you.